Tonight, we're going to explore something that sounds like an engineering problem, but is actually something much deeper: the challenge of reaching another star. Even our closest one. We've sent spacecraft to every planet in our solar system. We've landed rovers on Mars, orbited Saturn, flown past Pluto, and there's this assumption that interstellar travel is just the next step, just a matter of building better rockets and waiting long enough. By the end of tonight, you're going to see why the distance to even our nearest stellar neighbor might represent a barrier that's woven into the fabric of the universe itself. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. In the vast cosmic ocean, where stars are separated by distances so enormous they defy comprehension, we actually have a relatively close stellar companion. Proxima Centauri sits 4.24 light-years away. It's part of the Alpha Centauri system, a triple star system that's been known to humanity for thousands of years. Ancient civilizations saw Alpha Centauri in the night sky. They charted its position, included it in their star catalogues, wove it into their mythologies. To the naked eye, Alpha Centauri appears as a single bright point of light in the southern sky. It's the third brightest star visible from Earth. You can't see it from most of the northern hemisphere, but from anywhere south of about 25 degrees north latitude, it's a prominent feature of the night sky. Only in the 1800s did astronomers with powerful enough telescopes realize that Alpha Centauri was actually two stars orbiting each other. Alpha Centauri A and Alpha Centauri B circle their common center of mass every 79.9 years. They're close enough that they gravitationally influence each other, locked in an eternal dance. Then, in 1915, an astronomer named Robert discovered a third star in the system. This one was much farther out, a small red dwarf that appeared to be gravitationally bound to the A-B pair. He named it Proxima Centauri because it was slightly closer to us than the other two. Proxima Centauri is a red dwarf, the most common type of star in the galaxy. It's much smaller than our Sun, only about 12.5% of the Sun's mass. It's also much cooler and dimmer, putting out only about 0.17% of the Sun's energy. If you replaced our Sun with Proxima Centauri, Earth would freeze solid. The star is so dim that despite being the closest star to us beyond our Sun, you can't see it with the naked eye. You need a telescope. In 2016, astronomers discovered a planet orbiting Proxima Centauri. They called it Proxima Centauri B. This planet orbits in what scientists call the habitable zone, the region around a star where liquid water could potentially exist on a planet's surface. This discovery generated tremendous excitement. A potentially habitable planet around our nearest stellar neighbor. It seemed almost too perfect. Media outlets ran stories about it. Scientists discussed sending missions there. The idea entered public consciousness that maybe, just maybe, Proxima Centauri B could be a target for future exploration. But there's a cruel irony here. Having a neighbor star 4.24 light-years away sounds close in astronomical terms. And it is close compared to most stars. The average distance between stars in our region of the galaxy is about 5 light-years. Some stars are hundreds or thousands of light-years away. The center of our galaxy sits about 26,000 light-years away. Other galaxies are millions or billions of light-years distant. So yes, 4.24 light-years is close. It's our nearest neighbor. It's right next door in cosmic terms. But that proximity is an illusion. It's a trick of perspective that makes us think closeness in space means the same thing it does on Earth. It doesn't. Let's talk about what 4.24 light-years actually means. A light-year is the distance light travels in 1 year. Light moves at about 186,000 miles, or about 300,000 kilometers per second. That's the fastest anything can move in our universe. Nothing with mass can reach this speed, and nothing, not even information, can exceed it. It's a fundamental speed limit built into the fabric of space-time itself. In 1 year, light travels about 6 trillion miles, or about 9.5 trillion kilometers. That's 1 light year. Proxima Centauri sits 4.24 light-years away. That's about 25 trillion miles, or 40 trillion kilometers. This is where human intuition completely breaks down. So let's try a different approach. Let's talk about speed and time. The fastest spacecraft humans have ever built is the Parker Solar Probe. Launched in 2018, it uses the sun's gravity to accelerate to incredible speeds. At its closest approach to the sun, it reaches about 430,000 miles per hour, or about 690,000 kilometers per hour. That's almost incomprehensibly fast by human standards. It's fast enough to travel from New York to Tokyo in less than a minute. But even at this incredible speed, how long would it take to reach Proxima Centauri? About 6,000 years. That's longer than all of recorded human history. And this is with our absolute fastest spacecraft, moving at speeds we can only achieve by diving close to the sun and using its gravity to accelerate. But Parker Solar Probe only reaches these speeds briefly, during its close solar approaches. For a journey to another star, we'd need to sustain high speed for the entire trip. Let's look at Voyager 1 instead, which has been traveling continuously since 1977. Voyager 1 is currently moving at about 38,000 miles per hour, or about 61,000 kilometers per hour. Still fast, but nowhere near Parker Solar Probe's maximum. At Voyager's speed, the journey to Proxima Centauri would take about 75,000 years, 15 times longer than all of recorded human history. This is the reality of interstellar distances with current propulsion. But wait, you might be thinking, we could go faster, right? We could build a faster spacecraft. We could use better propulsion. We could accelerate to higher speeds. This is where we run into the fundamental problems. This is where the universe starts saying no. Let's talk about why we can't just go faster. Right now, the fastest spacecraft we've built use chemical rockets or gravity assists from planets. Chemical rockets work by burning fuel and expelling it out the back at high speed. The reaction pushes the spacecraft forward. It's basic physics, Newton's third law. Every action has an equal and opposite reaction. Push mass out the back, and the spacecraft moves forward. It's conceptually simple, but there's a brutal constraint called the rocket equation, also known as the Tsiolkovsky rocket equation. This equation describes the relationship between the mass of your spacecraft, the mass of your fuel, and the velocity change you can achieve. And it's not a friendly equation. To go faster, you need more fuel. But fuel has mass, and that mass needs more fuel to accelerate it, which adds more mass, which requires even more fuel. It's exponential. The amount of fuel you need grows exponentially with the speed you want to achieve. For small velocity changes, this isn't too bad. The Saturn V rocket that launched the Apollo missions was about 98% fuel to send 2% to the moon, and the moon is close, only about 240,000 miles away. To reach the speeds needed for interstellar travel, the fuel requirements become absurd. At 10% of light speed, which would still take over 40 years to reach Proxima Centauri, you'd need a fuel tank larger than a planet to accelerate a spacecraft the size of a car. The physics simply doesn't work. Chemical rockets cannot reach the speeds needed for interstellar travel. So what about other propulsion methods? What about nuclear propulsion? Surely, nuclear energy has much higher energy density than chemical fuel. It does. Nuclear reactions release millions of times more energy per kilogram than chemical reactions. This is why nuclear power plants can run for years on relatively small amounts of fuel. Why nuclear weapons are so devastating. The energy density is incomparably higher than anything chemical. There have been proposals for nuclear rockets going back to the 1950s. Project Orion, proposed in the late 50s and early 60s, would have used nuclear explosions to propel a spacecraft. Yes, nuclear explosions, actual atomic bombs. The idea was simple in concept, but insane in execution. You'd build a massive spacecraft with a thick steel plate on the back. This plate, called a pusher plate, would be attached to the spacecraft through enormous shock absorbers. Then, you'd drop nuclear bombs out the back of your spacecraft and detonate them. The explosion would hit the pusher plate. The shock absorbers would absorb most of the impact, converting the violent explosion into steady acceleration. Then, you'd drop another bomb, another explosion, another push, over and over again. Drop a bomb, let it explode, absorb the push, repeat. It sounds completely insane, and in many ways, it was. But the physics actually works. Engineers at Los Alamos National Laboratory and General Atomics worked on this seriously. They ran calculations, they built models, they even did some small-scale tests using conventional explosives. The concept was technically feasible. Engineers who worked on Project Orion calculated that such a spacecraft could potentially reach a few % of the speed of light, maybe 3 to 5% with a really good design. At 5% light speed, you could reach Proxima Centauri in about 85 years. Still longer than a human lifetime, still multiple generations, but at least within the realm of conceivability for a multi-generational mission. The spacecraft would be massive, thousands of tons, large enough to carry a crew, life support systems, radiation shielding, and thousands of nuclear bombs for propulsion. One proposed design had a diameter of about 20 meters, about 65 feet across. The pusher plate alone would weigh hundreds of tons. It would need to withstand the thermal and mechanical shock of nuclear explosions going off a few hundred feet away, over and over again. The spacecraft would accelerate in pulses. Each bomb would give a jolt of acceleration. The shock absorbers would smooth it out, but the crew would still feel it. But Project Orion was never built. The engineering challenges were enormous, yes, but they weren't the main reason it was cancelled. The real problems were political and legal. First, you'd need thousands of nuclear bombs. At the height of the Cold War, building thousands of additional nuclear weapons for a spacecraft raised obvious concerns. Who controls them? What if the spacecraft malfunctions during launch? What if it crashes back to Earth? You'd have thousands of nuclear devices scattered across the planet. Second, there's the environmental problem. Each detonation would produce radioactive fallout. Launching a Project Orion spacecraft from Earth would require dozens or hundreds of nuclear explosions just to reach orbit. The environmental and health consequences would be severe. Third, and most decisively, the Partial Nuclear Test Ban Treaty of 1963 banned nuclear explosions in the atmosphere, in space, and underwater. Only underground tests were permitted. Project Orion, which required exploding nuclear bombs in space, became illegal under international law. The project was cancelled. The engineers moved on to other things. And Project Orion became a fascinating what-if in the history of spaceflight. There have been other nuclear propulsion concepts since then. Project Daedalus, designed by the British Interplanetary Society in the 1970s, proposed a nuclear fusion rocket. Instead of fission bombs like Orion, it would use fusion reactions. The spacecraft would carry pellets of deuterium and helium-3 isotopes that can undergo fusion. It would fire these pellets into a reaction chamber and hit them with electron beams to compress and heat them. The fusion reaction would release enormous energy. The hot plasma would be directed out the back, producing thrust. The design showed it could accelerate to about 12% of light speed. A journey to a nearby star would take about 50 years. This is better than Orion. Faster travel time. No fission bombs, with their radioactive fallout. Cleaner, more elegant. But Daedalus was only ever a design study, a thought experiment. It was never built, not even close. The engineering challenges it faced were even more severe than those of Orion, because we don't have working fusion reactors, not for power plants on Earth, not for anything. We've been trying to achieve controlled fusion for over 70 years. The first hydrogen bomb was tested in 1952. That's uncontrolled fusion, a weapon. Controlled fusion, where you extract energy steadily and safely, has proven far more difficult. The basic problem is that fusion requires extreme conditions, temperatures of millions of degrees, pressures far beyond anything found naturally on Earth. At those temperatures, matter becomes plasma, and plasma is extraordinarily difficult to contain. It's electrically charged. It's hot enough to vaporize any material it touches. You can't put it in a metal container. The only way to contain it is with magnetic fields. Tokamaks, the most common fusion reactor design, use powerful magnetic fields to hold the plasma away from the walls. But maintaining stable plasma is incredibly difficult. Instabilities develop. The plasma can develop kinks and disruptions. It can cool down or lose confinement. The largest fusion experiments, like ITER, currently under construction in France, are enormous facilities. ITER will weigh about 23,000 tons. It requires massive superconducting magnets cooled to near absolute zero. It needs sophisticated control systems. It will consume enormous amounts of power. And even when it's completed, it's designed only to demonstrate net energy gain for short periods. Not continuous operation, not power generation, just proof that controlled fusion is possible. We're still years or decades away from practical fusion power plants on Earth. Building a compact fusion drive for a spacecraft? That's far beyond our current capabilities. It might always be beyond our capabilities. The mass and complexity of fusion systems might make them impossible to miniaturize for spacecraft use. Project Daedalus assumed breakthroughs in fusion technology that haven't happened and might not happen. It assumed helium-3 fuel, which is rare on Earth, but might be mined from the Moon or from gas giants. But mining helium-3 from space adds another layer of complexity. You'd need to establish mining operations on the Moon, or send spacecraft to Jupiter to extract helium-3 from its atmosphere. This is infrastructure that doesn't exist and won't exist for decades at minimum. So nuclear fusion, propulsion, while theoretically more promising than chemical rockets, faces enormous practical barriers. It's not something we can build now. It's not something we're likely to build in the next few decades. It requires technologies we don't have and might never have. And even if we did build it, even if we solved all the fusion problems, 12% light speed still means a 50-year journey. That's still longer than most human working careers. Still a lifetime. The people who design and launch the mission would likely be gone before it arrives. So nuclear propulsion, both fission and fusion variants, remains in the realm of theoretical proposals and engineering studies. Not actual hardware, not real missions, just ideas on paper that face insurmountable obstacles. What about light? Sails? This is perhaps the most actively discussed concept for interstellar travel right now. There's a project called Breakthrough Starshot that's gotten a lot of attention in recent years. It was announced in 2016 by physicist and investor Yuri Milner, with support from Stephen Hawking and Mark Zuckerberg. The idea is to use powerful lasers to push tiny spacecraft equipped with reflective sails. Light has momentum. When photons hit a reflective surface, they impart a tiny push. This is called radiation pressure. It's incredibly weak, but it's real. You can use it for propulsion. Solar sails have been tested in space. Japan's Icarus spacecraft, launched in 2010, successfully demonstrated solar sail propulsion. It used sunlight for thrust. But sunlight is weak and gets weaker the farther you get from the sun. So, Breakthrough Starshot proposes something different. Instead of using sunlight, use lasers. Powerful lasers based on Earth. You'd build an array of lasers on Earth, focus them on a tiny probe equipped with a reflective sail, and accelerate it to about 20% of light speed. At that speed, it could reach Proxima Centauri in about 20 years, plus another 4.24 years for the signal to return. So about 24 years total before we'd get data. That's within a human lifetime. The people who launched the mission could potentially see the results. This sounds promising. It sounds achievable. But when you dig into the details, the challenges are staggering. First, the laser array would need to be enormous and incredibly powerful. Breakthrough Starshot estimates you'd need about 100 gigawatts of laser power. 100 gigawatts. That's roughly the output of 100 nuclear power plants running at full capacity, all focused into a laser beam. Actually, not one laser, but thousands of individual lasers working in perfect synchronization. You'd need them spread over a large area, maybe a square kilometer or more. Each laser would need to be precisely aimed. They'd all need to fire at exactly the same time, with their beams combining coherently. Any misalignment, any timing error, and the power doesn't combine properly. The beam doesn't focus correctly. The efficiency drops. Building this laser array would cost tens of billions of dollars at minimum. It would be one of the largest engineering projects in history. You'd need to generate 100 gigawatts of power. That's more than the total power generation capacity of many countries. You'd need to convert it efficiently to laser light. Current laser systems are maybe 20 to 40% efficient. So you'd need to generate several hundred gigawatts of electrical power. Where does that power come from? Solar panels covering square kilometers? Nuclear reactors? The infrastructure required is immense. Second, you need to focus all that power on a sail that's only a few meters across. The sail would be tiny. Current designs envision a sail about 4 meters by 4 meters, about 13 feet on, aside. That's the target for 100 gigawatts of laser power. The intensity would be beyond anything we've ever created. The sail would need to be made of some material that can reflect the laser light without absorbing any of it. Because any absorbed energy becomes heat, and at these power levels, even a tiny fraction of absorbed energy would vaporize the sail instantly. The sail would need to reflect 99.999% or more of the light. Any less, and it burns up. We don't currently have materials that can do this for the high power densities required. Research is ongoing, but it's not clear such a material is even possible. Third, there's the atmosphere problem. The laser beam has to pass through Earth's atmosphere. The atmosphere distorts light. Anyone who's looked at stars twinkling knows this. That twinkling is atmospheric turbulence, bending and scattering starlight. For a laser beam carrying 100 gigawatts, atmospheric distortion is a huge problem. The beam spreads out. It loses focus. Power is wasted. You'd need adaptive optics, systems that measure the atmospheric distortion in real time and adjust the laser beam to compensate. This technology exists for telescopes. But scaling it to 100 gigawatts over thousands of propulsion lasers? That's another enormous challenge. You'd probably need to build the laser array at a high altitude, dry location, somewhere with thin, stable atmosphere, maybe on a mountaintop in the Atacama Desert or somewhere similar. Even then, atmospheric conditions would limit when you could fire the lasers. Clouds would make it impossible. Too much humidity would cause problems. You'd have weather-dependent launch windows. Fourth, tracking. Once you start accelerating the sail, it's moving fast. It accelerates from 0 to 20% of light speed in a matter of minutes. The laser beam needs to stay focused on the sail during this entire bright acceleration. But from the perspective of Earth, the sail is moving away at increasing speed. It's getting farther away. The targeting becomes more and more difficult. Any error, any wobble in the sail, any slight misalignment, and the beam misses. You lose thrust. The mission fails. The tolerance is incredibly tight. At the distances involved, even a tiny angular error means the beam misses by meters or more, and the sail itself might not be perfectly stable. It might flutter or tumble as it's hit by asymmetric light. Pressure. Keeping it oriented correctly during acceleration is a significant challenge. Fifth, the probe itself would have to be incredibly small and light. The current concept envisions something called a star chip, a spacecraft weighing about 1 gram. 1 gram. That's less than a sugar packet. That's about the weight of a paperclip. Everything the mission needs has to fit in 1 gram. Camera, maybe a very small one, with minimal resolution. Communication system to send data back across 4 light years. That's going to be extraordinarily difficult. You need a transmitter. You need power to run it. You need an antenna to send a directional signal toward Earth. All in 1 gram. Power. Source. Solar panels don't work well at Proxima Centauri because it's a dim red dwarf. The star puts out only about 0.17% as much energy as the Sun. Solar panels large, enough to power the spacecraft, would weigh far more than 1 gram. A battery? Batteries heavy enough to power a transmitter for years would weigh kilograms, not grams. A radioisotope thermoelectric generator, like the ones used on deep space probes like Voyager and Cassini, those weigh tens of kilograms and use plutonium. You can't miniaturize them to 1 gram. So where does the power come from? There's no good answer yet. The mission might rely on some future breakthrough in ultra-efficient electronics and ultra-lightweight power systems. But those don't exist now. And it's not clear they can exist at the scale needed. Computer? The Starship needs onboard computing to control the camera, manage data, compress it, and transmit it. All in 1 gram. Modern computer chips are small, yes, but they still weigh more than 1 gram when you include packaging and support circuitry. And they need power, sensors, any scientific instruments to measure the environment, detect magnetic fields, analyze particles, measure radiation. All need to fit in 1 gram. The engineering challenges of cramming all this into 1 gram are extraordinary. It might not be possible. Sixth, and this is critical, there's no way to slow down. A light sail works by having light push against it. To slow down, you'd need light pushing from the opposite direction. But there's no laser array at Proxima Centauri to slow you down. The probe would scream past the star system at 20% light. Speed, about 37,000 miles per second, about 134 million miles per hour. At that speed, you'd cross the distance from Earth to the Sun in about 20 minutes. The entire Proxima Centauri system, from the outer reaches to the star and back out, you'd traverse in a matter of hours or days at most. You'd get a brief window to collect data, take pictures, make measurements, and then you'd be gone, hurtling deeper into interstellar space with no way to stop. No orbiting, no detailed study, no landing on any planets, just a high-speed flyby. All the effort, all the cost, for a few hours or days of data collection. Some have proposed ways around this. Maybe the probe could carry a second, smaller sail. During the flyby, it could deploy this second sail ahead of it, letting starlight from Proxima Centauri push against it to slow down. But the numbers don't work out. Proxima Centauri is too dim. Its starlight isn't strong enough to slow a probe. From 20% light speed to orbital velocity in the brief time available, the probe would still fly past before slowing significantly. Other proposals involve magnetic sails that interact with the interstellar medium to provide drag. But again, the interstellar medium is incredibly tenuous. 1 hydrogen atom per cubic centimeter isn't enough to provide meaningful drag at reasonable timescales. So the no deceleration problem appears fundamental. Breakthrough Starshot, if it works, would be a flyby mission. Not an orbiter, not a lander, a flyby. Seventh, communication. This might be the most insurmountable problem of all. To send data back to Earth, the Starship needs a transmitter with enough power to send a signal across 4.24 light-years. The signal strength drops off with the square of the distance. Double the distance, the signal becomes 1/4 as strong. 4.24 light-years is about 25 trillion miles. A signal from Proxima Centauri would be unimaginably weak by the time it reaches Earth. To receive it, we'd need enormous radio telescopes, arrays of dishes working together, and the Starship would need to transmit at high power. But power is the problem. A 1-gram spacecraft doesn't have a power source capable of running a transmitter strong enough to send signals across interstellar distances. Voyager 1, our most distant spacecraft, transmits at about 23 watts. That's the power of a small light bulb, and it has a 3.7-meter dish antenna to focus the signal. Even with this, Voyager's signal is barely detectable on Earth, and it's only about 15 billion miles away. That's about 60 times closer than Proxima Centauri. The signal strength falls off with the square of distance. So at Proxima Centauri's distance, Voyager's signal would be about 3,600 times weaker than it is now. Already, we need 70-meter radio telescopes to detect Voyager's signal. To detect a signal from Proxima Centauri, we'd need dishes hundreds of meters across, or arrays of many dishes working together. And that's if the probe can transmit at 23 watts. But Voyager weighs about 820 kilograms. The Starship weighs 1 gram. It has nowhere near the power capability. If it can transmit at all, it might be milliwatts, thousandths of a watt. The signal would be so weak it might be impossible to detect even with the largest radio telescopes. The data rate would be extremely low, maybe a few bits per second at best. Transmitting a single image could take days or weeks, and you only have hours or days during the flyby. The communication problem might be unsolvable with a 1-gram probe. You might need a heavier probe with more power. But a heavier probe is harder to accelerate. You need more laser power, which makes the ground system even more expensive and complex. It's a catch-22. Finally, even if you solved all these problems, even if you built the laser array and launched the Starship and received data from its flyby, you're still looking at decades before you learn anything. The probe takes 20 years to get there. The signal takes 4 years to get back. That's 24.24 years minimum. But realistically, you'd want to collect data for more than just a few hours. You'd want to transmit images, scientific measurements, atmospheric data if the planet has an atmosphere. All of that takes time to transmit at the low data rates available. So you're looking at 25 to 30 years before you start seeing substantial results from a mission launched today. A quarter century. The scientists who design the mission might be retired before the data arrives. The engineers who build the hardware might not be working in the field anymore. The entire mission team would turn over, possibly multiple times. Breakthrough Starshot is working on these problems. They've made progress. They've demonstrated some of the individual technologies needed, but putting it all together, building the actual system, launching an actual mission, that's still decades away. Maybe it will happen. Maybe in 30 or 40 years, we'll launch the first Starship toward Proxima Centauri. But it's not guaranteed. The technical challenges are immense, the costs are enormous, and the payoff, while scientifically valuable, is limited. A brief flyby, a few pictures, some measurements, that's all you get for decades of work and billions of dollars. It might still be worth doing, but it's not. The interstellar exploration that science fiction has promised us. It's not sending humans to another star. It's not even sending a robotic probe that can orbit and study the system in detail. It's a glimpse. A quick look as we fly past at incredible speed. Better than nothing, but far from the dream of reaching the stars. What about generation ships? Build an enormous self-sufficient spacecraft, put hundreds or thousands of people on it, and launch it toward Proxima Centauri. The journey would take centuries. The people who launch won't arrive. Their children won't arrive. Maybe their distant descendants will. It's appealing because it seems possible without exotic physics. Just a big ship, and people willing to commit their descendants to the journey. But the problems are overwhelming. Start with social challenges. You're asking people to live their entire lives on a spacecraft, never seeing the destination. What motivates the 10th generation to continue a mission started by ancestors they never knew, toward a destination they'll never see? Human societies change dramatically over centuries. Languages evolve, cultures transform, values shift. What happens to an isolated society on a spacecraft for 500 years with no contact from outside? There's no historical precedent. Social conflicts, power struggles, or rebellions could be catastrophic on a spacecraft where everyone depends on critical systems functioning perfectly. Then, biological challenges. A generation ship would use rotation for artificial gravity. But we've never studied humans living in artificial gravity for entire lifetimes. Does bone density develop normally? Does reproduction work the same? We don't know. Radiation is enormous. Without Earth's magnetic field, the ship would be bombarded by cosmic rays for centuries. Higher cancer rates, genetic mutations, shorter lifespans. Heavy shielding adds mass, making acceleration harder. Genetic diversity is critical. A founding population of a few hundred people breeding among themselves for centuries leads to inbreeding and loss of genetic diversity. Population geneticists estimate you need several thousand individuals, minimum, for long-term genetic health. Resource sustainability requires a completely closed ecosystem where everything is recycled perfectly. We tried this with Biosphere 2, 8 people for 2 years. It failed within months. Oxygen dropped. They had to pump in air from outside. A generation ship needs this to work for thousands of people for centuries. Technical knowledge must be preserved. If a critical system works perfectly for 3 generations, does the 4th generation remember how to fix it when it breaks? Knowledge degrades when not used regularly. We've lost ancient technologies on Earth for exactly this reason. The generation ship concept is romantic, appealing to our sense of adventure. But we've never built a closed ecosystem that works beyond months. We've never had humans in artificial gravity long term. We've never maintained an isolated society for centuries. All unsolved problems. Anyone could doom the mission. The generation ship might remain forever in science fiction. What about cryogenic sleep or suspended animation? The idea here is that you freeze the crew or slow their metabolism to near zero, then wake them up when you arrive. This solves the generation problem. The same people who launch would arrive. It solves some of the social problems because you're not asking people to raise children on a ship for a mission they'll never complete. It potentially reduces life support requirements because frozen or suspended people don't need food, water, or air. But cryogenic sleep remains pure science fiction. We can't do it. We've frozen human embryos successfully. We've frozen eggs and sperm. We've even frozen some tissues and organs for short periods. But we cannot freeze an entire living human and then revive them. The problem is ice crystals. When water freezes, it forms crystals. Those crystals have sharp edges. They puncture cell membranes. They destroy cellular structures. When you freeze a piece of meat and then thaw it, the texture changes because ice crystals have damaged the cells. The same thing happens in human tissue. Some animals can survive freezing. Wood frogs, for instance, can freeze solid during winter and then thaw out in spring. But they've evolved specialized proteins that prevent ice crystal formation. Their cells produce glucose and urea that act as cryoprotectants. Humans don't have these adaptations. We haven't evolved to freeze and revive. And artificially adding cryoprotectant chemicals to every cell in a human body is extraordinarily difficult. You'd need to perfuse the entire body with cryoprotectants, replace all the water in every cell. This has been tried with laboratory animals. The results are not encouraging. Some research has managed to freeze and revive small organs or tissue samples. But scaling that up to an entire human body is a completely different challenge. Even if you solve the freezing problem, you'd still need to solve the revival problem. How do you warm the body evenly? If you warm too slowly, ice crystals grow larger and cause more damage. If you warm too quickly, you get thermal stress that can crack tissues. You'd need to warm every part of the body at exactly the right rate. And then, once the body is thawed, you need all the cellular machinery to start working again. Every enzyme needs to function. Every ion channel needs to open and close properly. Every nerve cell needs to fire correctly. The brain needs to resume normal electrical activity. This is far beyond our current medical capabilities. It might be fundamentally impossible. There's another approach called suspended animation that doesn't involve freezing. Instead, you cool the body to just above freezing and slow metabolism to almost nothing. Some research in emergency medicine has experimented with this for trauma patients. By cooling them rapidly, doctors can slow cellular damage and buy time for surgery. But this works for hours, not years or decades. No one has successfully kept a human in suspended animation for more than a few hours. And even those few hours cause complications. Extending it to years or centuries? We don't know how. Every biological process in your body depends on constant activity. Your cells are constantly repairing damage. Your immune system is constantly fighting off infections. Your nervous system is maintaining itself. Stop all that activity, and damage accumulates. Even if your metabolism is slowed, it's not stopped. Radiation still damages DNA. Chemical reactions still occur, just more slowly. Over years or decades, the cumulative damage could be lethal. So cryogenic sleep and suspended animation, while popular in science fiction, are not viable solutions with current technology or any technology we can foresee. This brings us to the fundamental physics barrier. This is where the universe itself says no. Everything we've talked about so far, slow spacecraft, engineering challenges, biological problems, these are all practical limitations. In principle, you could imagine some future civilization solving them. Maybe in 1,000 years. Humans will have fusion drives and closed-loop ecosystems and suspended animation. Maybe. But even if you solve all the practical problems, there's still a wall you can't get past. The speed of light. Einstein's theory of special relativity shows that nothing with mass can reach the speed of light. Not almost reach it. Not asymptotically approach it. Actually cannot reach it. This isn't a limitation of our engineering. This is a law of physics. Here's why. As an object with mass accelerates, its mass effectively increases from the perspective of a stationary observer. The faster you go, the more massive you become. This is called relativistic mass. At low speeds, this effect is negligible. A car traveling at 60 miles per hour weighs essentially the same as a stationary car. But as you approach the speed of light, the mass increase becomes dramatic. At 90% of light speed, your mass is about 2.3 times your rest mass. At 99% of light speed, your mass is about 7 times your rest mass. At 99.9% of light speed, your mass is about 22 times your rest mass. And as you get closer and closer to light speed, your mass approaches infinity. To accelerate mass, you need energy. More mass requires more energy. If your mass is approaching infinity, the energy required to accelerate you further approaches infinity. You cannot generate infinite energy. Therefore, you cannot reach light speed. This is why physicists say that light speed is a universal speed limit. It's not that we haven't figured out how to go that fast yet. It's that the laws of physics prohibit it. Even if you had a perfect engine with perfect fuel efficiency, even if you could somehow convert mass directly into thrust with 100% efficiency, you still couldn't reach light speed because the energy requirements become infinite. This creates a brutal constraint on interstellar travel. Let's say you wanted to reach 99% of light speed. That's fast enough that relativistic effects become important. Time dilation would mean that the journey feels shorter for the travelers than for people back on Earth. At 99% light speed, you could reach Proxima Centauri in about 4.3 years of Earth time. But from the perspective of the travelers, only about 7 months would pass. Time dilation is real. It's been measured countless times. GPS satellites have to account for it. Particle accelerators observe it every day. So, 99% light speed would make the journey feel relatively short for the crew. But how much energy would you need to accelerate a spacecraft to 99% light speed? Let's take a small spacecraft, say 1,000 kilograms. That's about 2,200 pounds, very small for a spacecraft that would need to support a crew. The kinetic energy of an object is given by relativistic equations. At 99% light speed, that 1,000 kilogram spacecraft would have kinetic energy of about 5.03 times 10 to the 20th joules. That's 3,000 trillion joules. To put that in perspective, the total annual energy consumption of all human civilization is about 6 times 10 to the 20th joules. So accelerating a 1,000 kilogram spacecraft to 99% light speed would require almost all the energy humanity uses in an entire year for one small spacecraft. And this is just to accelerate it. If you want to slow down when you arrive, you need to expend the same amount of energy again. So now you're looking at 2 years' worth of total human energy output to send one small probe on a one-way trip with deceleration. This is absurd. We're not talking about the energy output of a power plant or even a country. We're talking about the entire energy budget of human civilization. And this is at 99% light speed. If you want to go even faster, say 99.9%, the energy requirements go up dramatically. At 99.9% light speed, the same 1,000 kilogram spacecraft would need about 1.58 times 10 to the 21 joules. That's about 2.6 years of total human energy output. And at 99.99% light speed, you'd need about 5 times 10 to the 21 joules, about 8.3 years of total human energy output for 1,000 kilograms. This is why speeds close to light speed are effectively impossible. The energy requirements are so high that you'd need to harness the entire output of multiple stars to achieve them. Some theoretical proposals, like the Kardashev scale, imagine civilizations that can harness the total energy output of their star or even their galaxy. But we're nowhere close to that. We're a Type 0.7 civilization on the Kardashev scale. We use only a tiny fraction of our planet's available energy. We're centuries, maybe millennia away from being able to harness the sun's total output. And even if we could, using years' worth of stellar energy output to send one small probe to a nearby star is an enormous investment for minimal return. There's another problem with traveling at relativistic speeds. Interstellar space isn't completely empty. There are atoms out there, hydrogen atoms mostly. about 1 atom per cubic centimeter on average. That doesn't sound like much. 1 atom per cubic centimeter is an incredibly good vacuum by Earth standards. But when you're traveling at 99% of light speed, every atom you hit becomes a high-energy particle. At those speeds, a hydrogen atom has the energy of a bullet. Your spacecraft would be bombarded constantly by what amounts to cosmic radiation, far more intense than anything we experience in the solar system. The cumulative damage would be enormous. You'd need shielding, which adds mass, which requires more energy to accelerate. And even with shielding, some particles would get through. Over years of travel, the damage could be catastrophic. This is yet another barrier to high-speed interstellar travel. So let's take stock of where we are. Chemical rockets can't reach the speeds needed. Nuclear propulsion might get us to a few percent of light speed, but we can't build it yet. Light sails have communication and deceleration problems. Generation ships face insurmountable social and biological challenges. Cryogenic sleep doesn't work. And traveling at relativistic speeds requires energy we can't generate. Every approach we can think of hits fundamental barriers. These aren't engineering problems waiting for better technology. These are physics problems with no solution in sight. This brings us to the cruel reality. We are isolated. Proxima Centauri is 4.24 light-years away. For all practical purposes, it might as well be infinite. We will never go there. Not with any technology we have. Not with any technology we can foresee. The universe has placed a wall around us. Not a wall of space, but a wall of speed and energy. We're confined to our solar system. And this isn't just our problem. If other civilizations exist around other stars, they face the same barriers. The physics is the same everywhere. The speed of light is constant throughout the universe. Energy requirements scale the same way for everyone. If there are intelligent beings around Proxima Centauri, they can't reach us either. They're just as isolated as we are. This is one possible answer to the Fermi paradox. Enrico Fermi famously asked, "Where is everybody?" If the galaxy is billions of years old and contains hundreds of billions of stars, many with planets, where are all the alien civilizations? Why haven't they contacted us? Why don't we see evidence of them? One answer is that interstellar travel is simply too hard. Maybe the galaxy is full of civilizations. Maybe there are thousands or millions of intelligent species out there, but they're all trapped in their home star systems just like us. They can see each other through telescopes. They can detect each other's radio transmissions if they're lucky. But they can't visit. The distances are too great. The speeds required are too high. The energy costs are too enormous. So the galaxy becomes a collection of isolated islands. Each island, inhabited, perhaps, but unable to communicate meaningfully with the others. Radio waves travel at the speed of light. A message sent to Proxima Centauri would take 4.24 years to arrive. A reply would take another 4.24 years to get back. That's an 8.48-year round-trip time for a single exchange. You couldn't have a conversation. You could exchange messages. But with nearly a decade between each exchange, it wouldn't be a dialogue. It would be more like leaving messages in bottles and hoping someone eventually reads them. And Proxima Centauri is our nearest neighbor. Most stars are much farther away. The average star is about 5 light-years away. Many interesting stars are dozens or hundreds of light-years away. Communication with those would take decades or centuries per exchange. This is the cosmic loneliness. We can see the universe. We can observe galaxies billions of light years away. We can detect planets around other stars. We can measure the composition of their atmospheres. We can learn an enormous amount about the cosmos, but we're stuck here. We cannot visit any of it. We cannot touch it. We cannot walk on a surface of an exoplanet. We cannot meet another civilization face to face. We're like someone locked in a room with a window. We can see out. We can see the world beyond the past and walls, but we cannot leave. The room is our solar system. The window is our telescopes, and the walls are made of physics. So what can we actually do? If interstellar travel is impossible, or at least so difficult it might as well be impossible, does that mean we just give up on exploring beyond our solar system? Not exactly. We can send robotic probes. The engineering challenges are still enormous, but they're less insurmountable than crewed missions. A probe doesn't need life support. It doesn't need food or water or air or comfortable temperatures. It doesn't need radiation shielding for biological organisms. It can be small and light. It can be built to withstand radiation that would kill a human. It can operate in extreme temperatures, extreme vacuum, for decades without maintenance. You can send it on a one-way trip with no expectation that it will ever return. And most importantly, you don't need to keep humans alive for the journey. Projects like Breakthrough Starshot are attempting exactly this. A tiny probe, weighing grams instead of tons, accelerated by lasers to 20% of light speed. It would take 20 years to reach Proxima Centauri. Then, a few more years for the signal to return. The data would be minimal because the spacecraft is so small. The flyby would be brief because there's no way to slow down. But it would be something. We'd get a close-up look at another star system for the first time in human history. We'd see Proxima Centauri B up close, not just as a data point detected by measuring the star's dimming or its wobble, but as an actual image. We'd know if it has an atmosphere, and if so, what's in it. We'd see what its surface looks like, whether it has oceans or continents or is barren like Mars. We'd know if it shows any signs of life, any hints of biological activity. That knowledge would be valuable, even if we could never go there ourselves, even if we could never set foot on its surface. Just knowing would change how we see ourselves. Are we alone? Is Earth special? Or is life common throughout the galaxy, just separated by distances we can't cross? The answer to that question matters deeply, even if we can never meet our neighbors. We can also continue to improve our telescopes, and we have been. The pace of improvement in the last few decades has been extraordinary. The Hubble Space Telescope, launched in 1990, revolutionized astronomy. It gave us images of unprecedented clarity because it sits above Earth's atmosphere. No atmospheric distortion, no weather, no light pollution, just pure, clear views of the universe. Hubble discovered that the universe's expansion is accelerating. It measured the age of the universe more precisely. It found black holes at the centers of galaxies. It showed us galaxies so distant their light has been traveling toward us for billions of years. Hubble's discoveries fundamentally changed our understanding of the cosmos, and now we have the James Webb Space Telescope, launched in December 2021. Webb is even more powerful than Hubble. Its mirror is much larger, 6.5 meters across, compared to Hubble's 2.4 meters. It observes in infrared light, which can penetrate dust clouds and see farther back in time. Webb can analyze the atmospheres of exoplanets. It can detect molecules like water vapor, carbon dioxide, methane, and oxygen. This is revolutionary. If we found oxygen and methane together in an exoplanet's atmosphere, that would be strong evidence of life. On Earth, oxygen is produced primarily by photosynthetic organisms, plants, and photosynthetic bacteria. It's reactive. It combines with other elements readily, so it doesn't stay in the atmosphere unless something is constantly replenishing it. On Earth, that something is life. Methane is also produced by biological processes. Bacteria produce it. Animals produce it. Some geological processes can produce methane, but biological production is common. Having both oxygen and methane together is particularly compelling because they react with each other. They shouldn't coexist in an atmosphere unless both are being constantly replenished. On Earth, this happens because life produces both. If we detected that signature on Proxima Centauri B or any other exoplanet, we'd have strong evidence that life exists there. We couldn't visit it. We couldn't study it up close. We couldn't communicate with it if it's just microbial life. But we'd know we weren't alone, and that knowledge would change everything. It would change philosophy, religion, our sense of ourselves. It would answer one of humanity's oldest questions: are we alone in the universe? Even without going there, even without touching it, that answer would be profound. Beyond studying distant exoplanets, we can also focus on building civilization within our solar system. And this is actually achievable. Not easy, not cheap, but achievable with technology we have or can develop in the near future. Mars is the obvious first target. Mars is harsh. The atmosphere is thin, mostly carbon dioxide. Only about 1% the pressure of Earth's atmosphere. You can't breathe it. The temperature averages around -80 degrees Fahrenheit or -62 degrees Celsius. At the equator in summer, temperatures might reach 70 degrees Fahrenheit or 21 degrees Celsius during the day, but they plunge to -100 degrees Fahrenheit or -73 degrees Celsius at night. There's no liquid water on the surface because the pressure is too low for liquid water to exist. The surface is bombarded by radiation because Mars has no global magnetic field and its thin atmosphere provides little protection. Dust storms can envelop the entire planet and last for months. It's not a hospitable place, but it's reachable. We've sent dozens of missions to Mars. We've landed rovers that have explored the surface for years. Opportunity operated for almost 15 years, far exceeding its planned 90-day mission. Curiosity has been exploring since 2012. Perseverance landed in 2021 and is collecting samples. We know how to get to Mars. We know how to land there. We know how to operate on its surface. Humans could go to Mars. The journey would take about 6 to 8 months with current technology. That's long, but it's achievable. It's within a human lifetime. You could launch a mission and see it succeed. The people who go to Mars would return to Earth, or if they chose to stay, they'd still be in communication with Earth. The light travel time is only about 3 to 22 minutes, depending on where Earth and Mars are in their orbits. You could have conversations with some delay, but it's manageable. Not the 4-year delays you'd have with Proxima Centauri. Minutes, not years. Mars has resources we could use. It has water ice at the poles and in the subsurface. You can melt this ice for drinking water. You can split it into hydrogen and oxygen for fuel and breathing air. It has carbon dioxide in the atmosphere that could be processed into oxygen and methane using energy and chemical reactions. This is called in situ resource utilization. using what's already there instead of bringing everything from Earth. It makes long-term habitation feasible. Mars has minerals and metals in its soil and rocks: iron, magnesium, silicon, sulfur, and more. You could potentially mine these and use them for construction and manufacturing. The gravity is 38% of Earth's gravity. That's not nothing. It's more than the Moon's 16%. It might be enough for human bodies to adapt without the severe problems associated with zero gravity. We don't know for sure, because no one has lived in Martian gravity, but it's plausible. With enough investment, with enough technology, humans could build habitats on Mars. Not just a small research station with a handful of astronauts, but actual settlements, communities, farms growing food in greenhouses, manufacturing facilities producing tools and equipment, power plants generating energy from solar panels or possibly nuclear reactors. It would be difficult. It would take decades to establish. The initial investments would be enormous, but it's possible. Not science fiction impossible, but hard engineering possible. And Mars is just the beginning. The moons of Jupiter offer incredible opportunities. Europa, one of Jupiter's 4 large moons discovered by Galileo in 1610, has a liquid ocean beneath its ice shell. The ice crust is probably 10 to 15 miles thick, maybe more. Beneath it is an ocean of liquid water, perhaps 60 miles deep. That's more water than all of Earth's oceans combined. And it's been liquid for billions of years, kept warm by tidal heating from Jupiter's gravity. Where there's liquid water, there's the possibility of life. On Earth, life exists everywhere. There's liquid water, in hot springs near volcanic vents, in deep ocean trenches where no sunlight penetrates, in Antarctic lakes buried under miles of ice, frozen lakes beneath glaciers. Anywhere water remains liquid, life finds a way. Europa's ocean might contain life, not necessarily complex life, probably just microbes, but life nonetheless. We could send a mission to Europa. NASA is planning the Europa Clipper mission, scheduled to launch in 2024. It will orbit Jupiter and make multiple flybys of Europa, studying the ice shell and the ocean beneath. But a flyby mission can only tell us so much. To really know if there's life, we need to get into that ocean. We need to drill through the ice, lower a probe into the water, and look. This is technically challenging, but feasible. You'd need a lander that can survive on Europa's surface, a drill that can penetrate miles of ice, a submersible probe that can explore the ocean, all operating autonomously because the radio delay to Jupiter is 40 to 50 minutes. You can't remotely pilot anything with that delay. The probe needs to make its own decisions. But we have autonomous submersibles on Earth. We have drilling technology. We can build this if we commit the resources, and the payoff would be extraordinary. Finding life in Europa's ocean would prove that life arose independently at least twice in our solar system. That would suggest life is common in the universe. If it happened twice in one solar system, it probably happens everywhere. Conditions are right. That wouldn't mean intelligent life is common, but it would mean we're probably not alone. Enceladus, a moon of Saturn, is similar to Europa. It has an ocean under its ice crust. We know this because the Cassini spacecraft detected water geysers erupting from the South Polar region. Liquid water from the Faun, the subsurface ocean, is being ejected into space through cracks in the ice. Some of this water freezes and falls back to the surface as snow. Some escapes into space and forms one of Saturn's rings. The geysers contain organic molecules, the building blocks of life. Cassini flew through the plume and analyzed its composition. Water, salt, silica, particles, indicating hydrothermal activity on the ocean floor, and organic compounds, including methane. Everything you need for life. We could send a mission to fly through these plumes and collect samples. Look for signs of biological activity. Maybe. Even find living microbes in the water droplets being ejected into space. You wouldn't even need to land or drill. The moon is delivering its ocean to you. Titan, Saturn's largest moon, is one of the most interesting places in the solar system. It's the only moon with a thick atmosphere, thicker than Earth's. The atmospheric pressure at Titan's surface is about 1.5 times Earth's surface pressure. The atmosphere is mostly nitrogen, like Earth's, but with methane instead of oxygen. And Titan has weather, clouds, rain, rivers and lakes and seas. Not water. It's far too cold for liquid water. The surface temperature is minus 290 degrees Fahrenheit, or minus 179 degrees Celsius, but it has liquid methane and ethane. These hydrocarbons are gases on Earth, but they're liquids at Titan's cold temperatures. Titan has lakes of liquid methane, rivers cutting through the landscape, seas in the polar regions, clouds that produce methane, rain. It's an alien water cycle, but it's a cycle nonetheless. Complex organic chemistry is happening in Titan's atmosphere. Ultraviolet light from the sun breaks apart methane molecules. The fragments recombine into more complex organic compounds. These rain down onto the surface, accumulating in dunes and lakes over billions of years. Titan's surface has been covered in organic material. It's a chemist's dream. We could explore Titan. NASA and ESA are planning the Dragonfly mission, a nuclear-powered drone that will fly through Titan's atmosphere and land at different locations. It will study the organic chemistry, look for signs of prebiotic chemistry, or possibly even life. Titan's thick atmosphere makes flight easy. A drone that would struggle in Earth's thin, high-altitude air can fly easily in Titan's dense atmosphere despite the low gravity. You could send submarines to swim in Titan's methane lakes, boats to sail its seas, drilling rigs to sample the ice crust looking for the water ocean that's suspected to exist beneath the surface. Titan is a world waiting to be explored, and it's in our solar system. We can reach it in about 7 years with current propulsion technology. The Cassini-Huygens mission proved this. Cassini orbited Saturn for 13 years. The Huygens probe landed on Titan in 2005 and sent back images, data. We can go back. We can explore it properly. Beyond the moons, there are the asteroids. The asteroid belt between Mars and Jupiter contains millions of asteroids. Some are small, just a few meters across. Some are large, hundreds of kilometers in diameter. They're made of rock and metal, the leftover building blocks from when the solar system formed. These asteroids contain resources: iron, nickel, platinum, gold, rare earth elements. Some asteroids are more valuable than entire national economies. A single metallic asteroid could contain more platinum than has ever been mined on Earth. We could mine these asteroids, send spacecraft to extract metals and bring them back to Earth, or use them in space for construction. Space-based manufacturing could use asteroid resources to build structures, spacecraft, habitats. This would reduce the need to launch everything from Earth, saving energy and cost. Several companies are working on asteroid mining technology. It's still in early stages, but it's technically feasible. The biggest challenges are economic, not physical. But as space industry develops, as more infrastructure exists in orbit, asteroid mining becomes more attractive. The outer solar system has more to offer. Uranus and Neptune are ice giants. They're poorly explored. We've only had one flyby mission to each. Voyager 2 inches, the 1980s. We know little about their atmospheres, their magnetic fields, their interiors. They have moons we've barely seen. Miranda, a moon of Uranus, has bizarre terrain suggesting a complex geological history. Triton, Neptune's largest moon, has nitrogen geysers and might have a subsurface ocean. We should send missions to explore these worlds properly. Orbiters, atmospheric probes, maybe even landers on the moons. The Kuiper belt beyond Neptune contains thousands of icy bodies. Pluto, explored by New Horizons in 2015, turned out to be far more interesting than expected. It has mountains made of water ice, nitrogen glaciers flowing across its surface, a thin atmosphere that freezes and falls to the ground as snow as Pluto moves away from the Sun in its elliptical orbit. New Horizons showed us that even cold, distant worlds can be geologically active and fascinating. There are many more Kuiper belt objects waiting to be explored, each one a time capsule from the solar system's formation. The solar system is vast. It contains 8 planets, hundreds of moons, millions of asteroids, billions of comets. There's enough here to explore for centuries, maybe millennia. We could build a thriving spacefaring civilization within our solar system without ever leaving it. Habitats on Mars, the Moon, orbital stations, floating cities in Venus's upper atmosphere where temperatures and pressures are Earth-like, mining operations in the asteroid belt, research bases on Europa and Enceladus studying subsurface oceans, colonies on Titan exploring its organic chemistry, scientific outposts throughout the solar system studying planets, moons, and the Sun itself. This is within reach, not next year, not next decade, but within this century or the next. It's achievable with technology we have or can develop. It doesn't require faster-than-light travel or exotic physics, just engineering, resources, and commitment. This is the future we can actually have. Not starships traveling between galaxies like in science fiction, not colonies on distant exoplanets light years away, but a real, vibrant human presence throughout our solar system. And from our solar system, we can observe the rest of the universe. We can build larger telescopes, interferometers, combining the light from multiple telescopes to create effective apertures, hundreds or thousands of 12 kilometers across. We could put telescopes in orbit around the Sun, out in the Kuiper belt, where there's no interference from planets. We could build telescopes on the far side of the Moon, shielded from Earth's radio transmissions. We could develop technology to directly image exoplanets, not just detect their presence, but actually see them. See their continents and oceans, if they have them. See their weather patterns. Look for signs of civilization. City lights on their night sides, atmospheric pollution from industrial activity. We could search for technosignatures, evidence of other technological civilizations. Not just radio signals like SETI has been doing for decades, but other signs. Artificial structures in space, Dyson swarms around distant stars, propulsion signatures from spacecraft, atmospheric pollution that could only come from industry. If other civilizations exist and have developed technology, they might leave traces we can detect. Even if we can't visit them, we could know they're there. We could try to communicate, sending messages and waiting years or decades for responses. It wouldn't be the instantaneous communication of science fiction, but it would be communication nonetheless. A dialogue spanning generations, slow but meaningful. This is exploration too. Not the physical exploration of planting flags and walking on alien soil, but intellectual exploration, understanding without touching, learning without traveling. It's not as visceral as stepping onto an alien world, but it's profound. It expands human knowledge and understanding. And maybe that's what we're really here to do. Not to conquer the universe, but to understand it. Not to spread physically across all of space, but to reach intellectually across all of space. To know what's out there, even if we can't touch it. To comprehend the cosmos, even if we're confined to one small corner of great. There's something profound about this limitation. Something that defines what it means to be human in this particular universe. We're conscious beings with the capacity to understand things we can never experience directly. We can comprehend the interior of stars, even though we'll never visit one. We can understand black holes, even though we can never survive close to one. We can grasp the size and age of the universe, even though we can only ever inhabit a tiny fraction of it. This ability to understand beyond our direct experience is uniquely human. No other species on Earth can do this. Other animals understand their immediate environment through direct interaction. A bird understands the sky by flying through it. A fish understands the ocean by swimming in it. But humans can understand the surface of Mars by analyzing photographs and data. We can understand the composition of distant exoplanets by studying the light that passes through their atmospheres. We can understand events that happened billions of years ago by looking at ancient light reaching us now. This is an extraordinary capability. It's what separates us from every other form of life we know. And it's precisely this capability that makes the limitation of interstellar travel both frustrating and meaningful. We're smart enough to know what's out there. We're capable enough to understand it in great detail. But we're constrained by the physics of the universe from ever visiting it. It's like being given the ability to read about every place on Earth in perfect detail, to see photographs and videos, to understand the culture and history, but never being able to leave your hometown. You'd know about Paris and Tokyo and the Amazon rainforest. You'd understand what makes them unique and beautiful, but you'd never walk their streets or smell their air or feel their ground beneath your feet. That's humanity's situation with the stars. We can see them, study them, understand them, but we can't go there. Some might find this depressing. A cosmic prison sentence, trapped in our solar system forever. But there's another way to look at it. We're living in a remarkable era. The first era in which humans have truly understood our place in the cosmos. For most of human history, people didn't know there were other stars like our sun. They didn't know about exoplanets or galaxies or the vast scale of the universe. They looked up at lights in the sky and made up stories about them. Gods and heroes and mythical creatures. We're the first generations to know what those lights actually are, to know that they're distant suns, many with their own planetary systems. To know that the universe is almost 14 billion years old and contains hundreds of billions of galaxies. To know our cosmic address with precision. This knowledge is recent. Just a few hundred years ago, we thought Earth was the center of everything. Just 100 years ago, we thought the Milky Way was the entire universe. Just 50 years ago, we had never detected a planet around another star. Now we've found thousands. We've measured their sizes, their masses, their atmospheric compositions. We've identified candidates that might harbor life, all within a single human lifetime. The pace of discovery has been extraordinary, and it's not slowing down. Every year we build better telescopes, develop better detection methods, analyze data more thoroughly. Every year we learn more about the universe beyond our solar system. We're learning about places we'll never visit, understanding worlds we'll never to walk on, mapping a cosmos we'll never fully explore physically. And that's okay, because the exploration that matters is the exploration of knowledge, the expansion of understanding, the growth of human comprehension. We're doing that now, in our lifetimes, at a pace that would have seemed miraculous to our ancestors. Consider what we've accomplished. We've sent spacecraft to every planet in our solar system. We've landed on Mars multiple times. We've orbited Saturn and Jupiter for years. We've sent a probe past Pluto to see what lies in the distant Kuiper Belt. We've detected gravitational waves from colliding black holes billions of light years away. We've photographed the shadow of a black hole's event horizon. We've mapped the cosmic microwave background, the afterglow of the Big Bang itself. We've determined that the universe is flat, that it's expanding, that this expansion is accelerating. We've found water on Mars, organic molecules on Enceladus, complex chemistry on Titan. We've discovered that planets are common, that most stars have them. We've identified potentially habitable worlds within 100 light years. All of this in just a few decades of serious space exploration. Our grandparents grew up in a world where space travel was science fiction. Now it's routine. Our children might grow up in a world where we've confirmed life exists on Mars or Europa, where we've detected biosignatures in an exoplanet's atmosphere, where we've perhaps received a signal from another technological civilization. These discoveries are within reach, not physically, going there and shaking hands with aliens, but knowing they exist, understanding that we're not alone, that life arose elsewhere, that intelligence emerged elsewhere. That would fundamentally change human civilization. It would answer questions people have asked for thousands of years, and we wouldn't need faster than light travel to do it. We'd need better telescopes and patient, careful analysis of the data. We'd need to keep doing what we're already doing. Just do it better. This is the paradox of our situation. We're capable of understanding far more than we can physically reach. Our minds can go where our bodies cannot. Our theories can explore where our spacecraft cannot. And perhaps that's exactly as it should be. Perhaps the universe is set up this way deliberately, not by some conscious design, but by the fundamental nature of physics. The same laws that make complex chemistry possible, that allow stars to form and planets to orbit stably, that permit life to arise and evolve. These same laws also limit how fast we can travel. The speed of light isn't an arbitrary restriction. It's woven into the fabric of space-time itself. It's connected to causality, to the relationship between energy and mass, to the structure of the universe. Changing it would change everything. A universe where you could travel faster than light might be a universe where chemistry doesn't work the same way, where stars don't burn stably for billions of years, where planets don't orbit in the stable patterns needed for life to evolve. We exist in this universe with these particular physical laws, and these laws both permit our existence and limit our expansion. We can understand this without resenting it. We can accept the limitation while still pushing against it as far as physics allows. We can explore our solar system thoroughly while observing the rest of the universe from afar. We can build a rich, complex, spacefaring civilization within the volume we can actually reach. And we can know about the rest. Study it, understand it, appreciate it. Find meaning in the knowledge itself, not just in physical presence. So maybe the answer isn't to mourn what we can't reach. Maybe the answer is to appreciate what we can. This requires a fundamental shift in perspective, a redefinition of what exploration means. For most of human history, exploration meant going somewhere, walking to the next valley, sailing to the next continent, climbing the highest mountain, reaching the poles, going to the moon. Physical presence was the goal. Being there, standing on the ground, planting a flag. That's how we measured success. That's how we defined achievement. But maybe that's too narrow a definition. Maybe exploration is really about knowledge, about understanding, about expanding the boundaries of what we know. And you don't necessarily need to go somewhere physically to expand that knowledge. We've learned more about the universe in the last century through telescopes than we learned in all previous human history through exploration. Hubble taught us more about the cosmos than all the spacecraft we've sent to planets. The Cosmic Microwave Background Telescope taught us about the Big Bang without going anywhere. Gravitational wave detectors taught us about colliding black holes, billions of light years away, by sitting on Earth and measuring incredibly tiny fluctuations in space-time. We measured the distance to galaxies millions of light years away. We determined the age of the Christ universe to within 1%. We mapped the large-scale structure of the cosmos, the filaments and voids that stretch across hundreds of millions of light years. We discovered that the universe is expanding and that the expansion is accelerating. We found thousands of exoplanets around other stars. We photographed the shadow of a black hole's event horizon. All of this without leaving our planet or our solar system. This is exploration. It's intellectual exploration rather than physical exploration, but it's no less profound. Maybe more profound because it's accessible. Physical exploration is limited to those who can travel, those who are trained astronauts or mountaineers or sailors. But intellectual exploration is available to anyone. You can look through a telescope, you can study the data, you can think about what it means. You can contribute to our collective understanding. Science is a collaborative endeavor spanning generations. Each generation builds on what the previous generation discovered. Isaac Newton said he stood on the shoulders of giants. He meant that his work was possible because of all the scientists and thinkers who came before him. Galileo and Kepler and Copernicus and countless others who figured out pieces of the puzzle. Newton put those pieces together in a new way. Then Einstein came along and built on Newton's work. And now physicists today build on Einstein's work. Each generation pushes the boundary a little farther, and we're part of that. Right now, today, we're part of the generation that's discovering the universe. We're part of the generation that found thousands of planets around other stars, that detected gravitational waves, that imaged black holes, that might discover life on Mars or Europa or Enceladus, that might find evidence of life on an exoplanet through atmospheric analysis. This is our contribution to the long arc of human knowledge. And future generations will build on what we discover. They'll have better telescopes, better instruments, better theories. They'll answer questions we haven't even thought to ask yet. But they'll start from where we left off. Our discoveries become the foundation for theirs. This is how humanity explores the universe. Not individually, but collectively. Not in single lifetimes, but across generations. We can't walk on the surface of Proxima Centauri B, but we can walk on Mars. We can explore Europa's ocean. We can fly through Titan's atmosphere. We can mine asteroids for resources. We can build space stations and habitats. We can create new homes for humanity in our solar system. Permanent settlements that future generations will expand. This isn't a limitation. It's not settling for less than we wanted. It's a direction. It's where we should focus our energy and resources and dreams. Not on impossible fantasies of interstellar travel, but on achievable goals within our cosmic neighborhood. Goals that are difficult but not impossible. Goals that will challenge us, push our technology, require dedication and sacrifice. But goals we can actually accomplish. We can become a multi-planet species within our solar system. We can spread human civilization across the solar system. Multiple worlds with human presence. Mars, the Moon, orbital habitats, maybe floating cities in Venus's clouds, research bases on the moons of Jupiter and Saturn. Each world different, each requiring different technologies and adaptations, each expanding the range of environments where humans can live. This diversity makes us more resilient as a species. If something catastrophic happens on Earth, an asteroid impact or a supervolcano or a pandemic or a nuclear war, humans elsewhere in the solar system survive. Our civilization continues. Our knowledge persists. This is the practical argument for becoming multiplanetary. But there's also something deeper, something about human nature. We're explorers. We're curious. We look at what's over the next hill and want to know what's there. That drive has taken us around the world, to the poles, to the deepest ocean trenches, to the moon. It won't stop. We'll keep exploring as far as we can reach. And our solar system, vast as it is, gives us room to explore for a long time. Centuries, maybe millennia. There's enough unknown territory here to satisfy our curiosity for generations. And while we explore our solar system physically, we can explore the universe intellectually. Better telescopes, showing us more distant galaxies. More sensitive detectors finding more exoplanets. More sophisticated analysis revealing more about their atmospheres and surfaces. Maybe eventually we find signs of life elsewhere. Maybe we detect artificial radio signals from another civilization. Maybe we see artificial structures around a distant star. Maybe we find biomarkers in an exoplanet's atmosphere that clearly indicate life. Any of these discoveries would fundamentally change how we see ourselves. We'd know. We're not alone. We'd know life arose elsewhere. We'd know intelligence emerged elsewhere. Even if we can never meet them, even if we're separated by light years, we can't cross. Just knowing would matter. It would shift our perspective. It would change our philosophies and religions. It would give us context for our own existence. Are we typical or unusual? Is our path common or rare? These questions have answers. And we might find those answers through our telescopes, even if we can never travel to confirm them in person. We can also reframe how we think about exploration. For most of human history, exploration meant going somewhere physically, crossing oceans, climbing mountains, reaching the poles, stepping on the moon. But there's another kind of exploration. Intellectual exploration, understanding without touching. We've mapped the cosmic microwave background, the afterglow of the Big Bang. We've detected gravitational waves from colliding black holes billions of light years away. We've photographed galaxies as they appeared when the universe was young. We've done all this without leaving Earth. We've done it with telescopes and mathematics and careful observation. This is exploration too. It's not as visceral as planting a flag on a distant world, but it's profound. It expands human knowledge. It reveals the universe to us. We can see Proxima Centauri through our telescopes. We can measure its light spectrum and determine what it's made of. We can detect its planets and study their orbits. We can analyze their atmospheres if they have them. We can learn an enormous amount without ever going there. And that learning is valuable. It tells us how common planets are. It tells us how common life might be. It tells us about the physics and chemistry of planet formation. It tells us about our own origins, because Earth formed the same way those distant planets did. Understanding them helps us understand ourselves. So while we cannot reach Proxima Centauri, we can study it. We can learn from it. We can add it to our growing understanding of the cosmos. And perhaps that's enough. Perhaps the universe is meant to be understood, not conquered. Perhaps the joy is in the learning, not the touching. This is a hard truth to accept. Humans are explorers by nature. We've always pushed boundaries. We crossed continents. We crossed oceans. We climbed the highest mountains. We dove to the deepest trenches. We went to the moon. The idea that there's a boundary we can't cross, a place we can't reach, it feels wrong. It feels like failure. But it's not failure. It's reality. The universe is governed by laws. Those laws don't care about our ambitions or our dreams. They simply are. The speed of light is what it is. Energy requirements scale the way they scale. Distance is distance. And 4.24 light-years is too far. We can rage against this limitation. We can dream up wild technologies that might somehow bypass it. Wormholes, warp drives, shortcuts through higher dimensions. These are fun to think about. They make for good science fiction. But there's no evidence any of them are possible. Wormholes, if they exist at all, would likely be microscopic and unstable. Warp drives require exotic matter with negative mass, which we've never observed and which might not exist. Higher dimensional shortcuts are pure speculation with no experimental support. We can fantasize about these things, but we shouldn't base our plans on them. We should base our plans on what we know is possible. And what we know is that Proxima Centauri is unreachable. This leaves us with a choice. We can despair about what we cannot do, or we can celebrate what we can do. We can look up at Proxima Centauri and feel sadness that we'll never walk on its planets. Or we can feel wonder that it can see it at all, that we can measure its distance, that we can detect its planets, that we can study its light and learn what it's made of. We are tiny creatures on a tiny planet. We live for only a few decades. Our civilization has existed for only a few thousand years, and yet we've reached out across 4.24 light-years with our telescopes and our mathematics. We've touched Proxima Centauri with our minds, even if we can't touch it with our hands. That's remarkable. That's something to celebrate. The universe is vast beyond comprehension. There are hundreds of billions of stars in our galaxy alone. There are hundreds of billions of galaxies in the observable universe. Most of them we will never reach. Most of them we'll barely be able to study. But we can see them. We can know they exist. We can understand, at least partially, how they formed and how they evolve. We can place ourselves within that vast cosmic context. We can know that we're part of something immensely larger than ourselves. And perhaps that knowledge, that understanding, is the real exploration. Perhaps the journey isn't about going somewhere. Perhaps it's about understanding where we are. We are here, on Earth, in the solar system, in the Milky Way galaxy, in a universe that stretches 93 billion light-years across. We cannot visit most of it. We cannot even visit our nearest stellar neighbor. But we can comprehend it. We can study it. We can appreciate its beauty and its vastness. We can feel humbled by our smallness and elevated by our ability to understand. That's the paradox of cosmic exploration. The farther we look, the smaller we become. But the more we understand, the larger our minds become. We shrink in physical significance as we grow in intellectual capability. And maybe that's the trade-off the universe offers us. You cannot go there, but you can know it's there. You cannot touch it, but you can understand it. The nearest star will remain forever beyond our reach. Proxima Centauri will never feel the footsteps of human explorers. Its planets will never be colonized by our descendants. We will never terraform them, or mine them, or build cities on them. They will remain distant points of light, data in our telescopes, entries in our catalogues, objects of study, but not of visitation. And we have to make peace with that. We have to accept that the universe is bigger than we can traverse. That knowledge has limits, not because we're not clever enough, but because physics imposes constraints, that some dreams, no matter how compelling, will remain dreams. But acceptance doesn't mean giving up. It means redirecting. We can't reach Proxima Centauri, but we can reach Mars. We can explore our solar system. It can build a future among the planets and moons that are actually accessible. We can continue to observe the universe from our small corner of it. We can keep learning. We can keep discovering. We can keep pushing the boundaries of knowledge, even if we can't push the boundaries of travel. That's the future we can actually have. Not starships traveling between galaxies. Not colonies on distant exoplanets, but a thriving human civilization within our solar system. Habitats on Mars and the moons of Jupiter and Saturn. Space stations in orbit. Asteroid mining operations. Scientific outposts studying the sun and the outer reaches of our system. And powerful telescopes, both in space and on the ground, looking outward, seeing farther, understanding more, learning about the universe we inhabit but cannot fully explore. This is our cosmic address, the solar system, third planet from the Sun, Milky Way galaxy, local group, Virgo supercluster, Laniakea supercluster, observable universe. We know where we are. We know what's around us. We know that. Proxima Centauri sits 4.24 light-years away, with at least one planet that might be habitable. And we know we'll never go there. That's our reality. It's not the reality we might have hoped for. It's not the reality science fiction promised us. But it's the reality physics gives us. And we have to live in it. The nearest star is impossibly far away. The universe has drawn a circle around us, not out of malice, not as a punishment, but simply because that's how the physics works. That's how space and time and energy relate to each other. We can understand these relationships. We can measure them. We can map them. But we can't change them. So we look up at Proxima Centauri on a clear night. We see it twinkling in the darkness. We know it's there. We know its planets are there. And we know that's as close as we'll ever get. A point of light in the night sky. A neighbor we can never visit. A destination forever out of reach. And somehow, we find peace with that. Because the universe is still beautiful. The night sky is still full of wonder, and understanding, even without touching, is its own kind of journey. Thank you for joining me on this exploration of why we can never reach our nearest star. If you found this journey meaningful, a like or subscribe would help this channel continue making these deep dives into the cosmos. And remember, the universe may place limits on where we can go, but it places no limits on what we can understand. The nearest star will always be beyond our reach, but it will never be beyond our wonder. Good night, and keep looking up, even at the places you can never touch.